Oklahoma. So today, I want to talk about something about the Riemannian manifold. So for the Riemannian manifold, so we look at the metric. The title will be manifold with positive or non-negative sectional curvature. So this is a plan, or this is the outline for this talk. So we look at one question. So ask maybe 60 years ago by Hoff. So the question is asking, so does S2 cross S2 admit a metric sectional curvature? So the question is very interesting because this is a four-dimensional manifold, and for the S2, so this is a round sphere, and this one has positive curvature. So you see for each S2 in the S2 cross S2, we have positive sectional curvature. So that means so they are the convex surface. So if you put a metric, so using the round metric and the most natural metric do not have a positive sectional curvature. So this is open. So for the four dimension. Okay, so this is still open. So we can look at the dimension smaller than 4. We look at the 2 dimension and the 3 dimension. So for the 2 dimension and the 3 dimension, so there are strong relation between topology and the sign of the curvature. So the positive curvature, so like the surface is convex. So for example, you look at the surface in the 3 space. So a closed surface has positive curvature. So in the surface case, the Gauss curvature is positive. So if and only if this is a sphere. So you see the sphere. So everywhere, so if you look at the flight, so if you look at the 2 plane, so that one actually has the sectional curvature equal to 0. So so this is a geometric meaning for the sector. So actually tell you how the surface curve in the 3 space. So the statement or the classification in the 2 dimensions so actually follows from the Gauss-Bonnet formula. So the Gauss-Bonnet formula so tells you the geometric property. So we have this equation here. So if you look at this equation, so we have the curvature. So this one is the sectional curvature or the Gauss curvature for the surface, and the M2 is the surface, and the dA. So this one is the surface area. So if you integrate, so we got a number from the left-hand side. So you see, surface is convex. So that means the sectional curvature, the function k is positive. We know this part is positive, right? And then the formula used. So this integral actually has some topological meaning. So this is equal to pi times a topological invariant of the surface. That one is called chi. So the chi is the Euler characteristic. So for example, for the sphere, so we have the chi one is equal to this one is equal to the 2. This means we have the positive number here. So you see for the sphere, so it is positive on the right-hand side. So this means we have a positive k everywhere. So if you look at other surface, look at the Euler characteristic, the chi of the torus. This one actually is equal to 0. So if you apply a formula to the torus, so you see this term is equal to So you see this term is equal to is equal to 0. So this means either you have k is 0 everywhere, or you have k positive somewhere. So that means you cannot have surface on the first. The Gauss curvature is positive everywhere. Otherwise, you would have the positive number on the left, but the topological invariant here just tells you the interval. So for in 2 dimensions, you just apply the Gauss-Bonnet formula. So it's formula here. And so now we look at the 3 dimensions. In the 3 dimensions, we also have the similar statement. So the statement says, so if you have the compact, the 3 manifold, so this positive curvature, the positive curvature just means the surface, the 3 manifold so is convex in the high dimension. So we have the classification. So if this one is the finite of the sphere, so this means if you look at the metric, so actually the metric looks like the sphere, the 3 sphere, and this is a finite quotient. So that means you may have something called a length space. Yeah, the finite. So this is called space. But if you assume the 3 has simple topology, then you only have the sphere. Okay, then we look at the proof. So the proof is much harder than the proof in the 2 dimension. In 2 dimensions, so that proof may go back to 200 years ago, and this one actually is very new. Maybe Richard Hamilton. So proved this about 30 years ago, and he used very different technique. So this technique is called the Ricci flow. So what is a Ricci flow? The Ricci flow is given by this differential equation. So you see the G, so on the sphere, and the G. So we are determining the shape of the 3. The metric gives you the shape of the 3 space. And so that's called the Ricci curvature, this term. So the Ricci curvature actually is the average of the sectional curvature. So this equation, so you deform, so this is the equation, so in time t, so it's arbitrary metric. So any metric you want, for example, you have the positive sectional curvature. Then you deform this metric according to the Ricci curvature, and then this gives you a family of the metric. And then Hamilton showed if you have Hamilton showed so if the initial metric has the positive sectional, then the family of this metric will converge, so like the sequence to some limit. So the limiting metric is actually the round metric on sphere. So this gives you information from the initial metric to the round metric in the sphere. So in particular, the topology cannot change along this deformation. In particular, in life, your manifold has to be a sphere. So if you if you have the non-trivial topology, then you may have the finite quotient of the sphere. So Hamilton proof is the breakthrough. We have a very old conjecture, so by Poincare. So the Poincare says, so some certain conditions, so ensure your manifold is diffeomorphic, it's a wrong. So the Hamilton, so he used the Ricci flow. So he initiated so this revolution to to prove the Poincare conjecture. And so maybe I think 10 years ago, about 9 or 10 years ago, Paramount make the significant breakthrough, and finally we can prove the Poincare conjecture. Okay, so this is for the this is for the 2-dimension and 3-dimension. So you see, we have if we have the positive curvature, the positive sectional curvature in 3-dimension. So actually the manifold is determined. So it's equal to, so the manifold is the 2-sphere or the 3-sphere. But the proof, I mean, quite different. So one is very simple, and another one you have to use a lot of things.
Can I ask a question here? So do you assume that the manifold you're dealing with evolves, it's an evolution manifold, it evolves with time? So that as it evolves, the metric changes by g of t. Is that what you're assuming here? Or?
Yeah, okay. So you see, so you start from any metric with a positive curvature on your manifold.
Yeah.
And then you change the metric. So this means you want to change the shape of the manifold, right?
Yeah.
The metric change. So for example, so if we draw a picture in the in 2-dimension, so you football at the beginning. This is I can only, so you see, for example, you have a football at the beginning, then you change this one by this equation. You got a family of the metric, and found out, so your metric is getting round and round, getting more round. Yeah, this is how you involve or deform your metric. Means you change the shape. Then at the end, so the metric goes to a round sphere. Yeah, you see the top. You see the manifold doesn't change. You only change the shape, right?
Yeah, by changing the metric. It looks like the heat equation.
This is exactly the heat equation. Yeah, right. Yeah, in the 2-dimension. So this equation in 2-dimension is actually the heat equation. So we have the Laplacian term, so on the right hand side. But in the 3-dimension, it's actually a system. Yeah, because Ricci has has 3. So this is the 3x3 matrix.
Yeah.
Any other questions?
I don't. You guys have got any questions so far? Yuji, any questions so far? Okay.
No. Okay. So now we look at the 4-dimension. So for the 4-dimension, so we see we don't have the nice classification result because we cannot answer the question by Hopf. So we don't know S2 cross curvature or not. But we can look at the example in 4-dimension. So okay, so these are examples in 4-dimension. So the first one is the sphere in the 4-dimension. And also we can compute the topology. Topology is given by, so here the topology is given by the homology group. Homology group. And for the S is the 4th sphere. And we have the the natural metric, so on S4 has the radius equal to 1. So this is just the generalized. So this is just the generalization at dimension 3-dimension and to 4-dimension. And the topology is quite simple. So the homology groups actually characterize the topological property. So so the H0 and H4. So this just means some environment in 0-dimension or in 4-dimension is equal to the integers. And another example is given by the CP. So this one is actually another example in in 4 dimensions. So starting from 4 dimensions, this is called the complex projective space. So for the complex projective space, so this one has a very natural metric. So this one actually is a homogeneous space. The homogeneous space means so you have some isometry. So for any 2 points, so the geometry for the geometry at different points looks the same. So if you want to start the geometry for this manifold, so you only have to look at points and the tangent space at that point. Okay, then we look at the topology. So you have the H2. So this means in 2 dimensions. So the homology group is given by V. And then we look at so these are only examples in 4 dimensions with positive sectional curvature. We can look at the topology in S2 cross S2, and so you can compute. So the S2 cross S2, we have the the H0 and H4 equal to Z. So this is not a big surprise because we already have S4 and CP2 has this property. So now you can look at the H2 here. So this is a 2-dimensional homology. So this one actually is generated by is given by Z plus Z. So the generator for each one, the generator of Z is given by each factor in S2. So you see the difference here. so you see the difference here. So you have for S4 you have the H2 equal to 0, and for the CP2 you have the H2 equal to Z, and then if you go to the S2 cross S2, so you have another factor. So the question, maybe this is a topological obstruction. The B2 just means the dimension or the rank of this side. So this is 2 here. So if this one makes the obstruction to the positive sectional curvature for S2 cross S2, but this is not a general obstruction in high dimension because in 6 dimension, so there is another manifold. So also has the H2 equal to the Z plus Z. Okay, so this is for positively curved manifold in low dimensions. So we have classification in 2 and 3, and we have one big open problem in 4 dimensions. Okay, then we can look at some general structure results for the positive non-negatively curved manifold. So for the non-negatively curved manifold, we have so the first result, the structure result, so tells you, so this is by if M is compact and the sectional curvature is bigger or equal to 0, then the Beatty number, so there is also a constant. So the C is a constant. So the C of M means the constant only depends on the dimension. So such that, so this is called the Beatty number. So yeah, we can go back to this. So you see the Beatty number is actually the rank of the homology group. So for example, for the S4, we have B0 and B4 have 0. And for the CP2, we have B1, B2, and B4 equal to 1. We have one copy of Z. And for the S2 cross S2, we have B0, B4 equal to 1, and B2, because we have 2 copies of Z, so the B2 is 2. Okay, so the Gromov, the theorem by says, so if you have the non-negative sectional curvature, so yeah, this is this is the condition weaker than the positive. Positive means the coefficient, even the f is not the integers. And also, so you see this from this theorem. So you the topology, so it's quite simple because the Beatty number actually tells you, so if you have the Beatty number large, so this means the topology is complicated. You have some control for the topology. And also the fundamental group has a generating set with at most Cn element. So this just means the fundamental group also simple because the generating set has a universal bound, only depends on dimension, the n here. Okay, so this is a Gromov. This is a theorem by the Gromov. So it tells you if you have this special metric, the topology cannot be very complicated. And another one is tells you the formation of the fundamental group. So this is by Chigger and Gromov. So the Chigger and Gromov prove if the M is compact and has a metric with non-negative sectional means the same condition here. So then there exists an abelian subgroup of pi1, so it's a fundamental group with finite index. The finite index means so that you have a subgroup in the pi1, and then you look at the quotient of pi1 over the subgroup. So then then the quotient is actually a finite group. So this is called the index. The subgroup of the quotient is called the index of the subgroup. So you see, so the pi1 cannot be very complicated because we already have the classification for the abelian group. So this means, the fundamental group is quite simple. Okay, so this is for the non-negatively curved manifold. So this means you have the sectional curvature bigger or equal to 0. So somewhere you may have a 0 curvature. So this means your manifold, so at some points may look very. So this is for the non-negative sectional curvature. If we look at the positive sectional curvature, so the top or the manifold is even restricted. It's more we have more restriction for the topology of the positively curved manifold. So these two are classical theorem of the positively curved manifold. I think maybe we have this theorem maybe 70 or 80 years ago. Okay, so the first one says the first one is given by Bonnet and Mills. So this theorem says so a manifold has a curvature metric with positive curvature. Then actually the fundamental group is finite. So this is much simpler than the activity case. And another theorem by the siege. The siege actually tells you in the even dimension, so if the manifold has a positive curvature, then the fundamental group actually so this means it's trivial. So if your manifold is orientable, so if the manifold is non-orientable, then you have the V2. So you see from this theorem, so from the second theorem, so the topology is very simple in the even dimension. So you only have two different choices. The one is the 0 and another one is V2. So for example, in the 4 dimension, so we have this example. So the S4 has the trivial fundamental group. So this is in this case. And in the second case, so if so you can take the quotient real projective space. So they call the RP4. So the RP4 is covered by S4, and for any one point in the RP4, there are 2 points in S4 corresponds to these points. So this one is not orientable. So the fundamental group is equal to 2. So you only have 2 elements. And in the odd dimension, so the positively curved manifold is all positively curved manifold is orientable, but the fundamental group is finite, like the length space. Okay, so this is for the general structure theorem for the positively or non-negatively manifold. We assume the manifold is compact. Okay, so then we look at some examples. So you see, we don't have much result for the topology of the manifold, and also there's no classification in the 4-dimension. So one difficulty for this problem for the positively curved manifold is there are few examples in to our knowledge, and also it is very difficult to find those. So we can go through. So we can review. So what kind of manifold for the positively curved manifold? So we have the first class. So as classical examples. So the classical examples, we have the sphere, and we have the complex or the quasi-projective space. So this is the projective space in even dimension. And we have another one called the Cayley plane. So this actually in the dimension equal to 16. So we have 3 different classes, classical examples called the rank 1 symmetric space, the compact rank 1 symmetric space. So these are examples we already know maybe for 100 years. And so now we look at examples other than this. So you see, for each one, this is called the symmetric space. The symmetric space means this manifold has a lot of symmetry. So then we can look at new examples for the large symmetric group. So we can look at the first class. This is the homogeneous space. The homogeneous space means in points, any 2 different points. So you have an asymmetry. So move. So you have 1 point here on your manifold, and then there's another. Then you have an asymmetry. Asymmetry means this is a transformation of the manifold, but keep the metric and move. So this asymmetry moves 1 point to another point, to any point on your manifold. So it implies the metric property at this point is the same as the metric at these points. So then we can look at the homogeneous space. So this means for the positively curved manifold. So you only to check the curvature condition at 1 point, either this one or this one. So we have the classification for the homogeneous space. So this is the classification. So other than the cross, we have the 12 dimension.
Chenxu, we can't hear you. Okay, now we can hear you. Yeah, because you were out of the you were out of the listener's window. You were out of the listener's window for some reason. Yeah, so maybe let's see. Log back in. Yeah. See. Yeah, Joe. Yeah, that's good. So go back and just a few, two slides or so.
Okay, go back to last. So which one?
Impact. Yeah, to other before this. Yeah.
Before this, okay.
Yeah.
This one.
Let's go back and see what's let's go back one more and see. Yeah, because they didn't hear any of these. Yeah, they didn't hear this. No, you can go forward.
Okay.
Yeah, here, this one.
For the homogeneous space, right?
Yeah.
Okay, so you have to close the Google Hangout, otherwise I hear you twice.
Yeah. Okay.
Okay, so we look at more examples. So we have the cross. These examples appear in all dimensions, like the sphere or the complex projective space. And we can look at the manifold with large symmetry group. So, for example, look at the homogeneous space. The homogeneous space means so you have two different. So there's one transformation. So from these points to another point, and this transformation preserve the curvature, the metric property. So in another sense, so if you want to study the metric property, so for example, you want to compute the sectional curvature, so you only have to do for one point. By this transformation, so you have the same property at other points. So this is a homogeneous space. And for the homogeneous space, so we have more examples. So this is called Okay, so we have examples given by Berger. So two example in 7 dimension, and example in 13 dimension. This is the odd dimension. And then we look at the even dimension. The even dimension, so we have a space. The one of the space has 1 in 6 dimension, and then 1 in 12 dimension, and 1 in 24 dimension. And there's another infinity family in dimension 7, so these are all of one of the space. So these are all examples we have for the homogeneous space. So we have two different classifications for the even dimension, and another one is for the odd dimension. So size normal example positively curved homogeneous space. Okay, then we can look at other constructions. So one construction is called the biquotient. So the biquotient is a generalization of the homogeneous space. So we can look at the homogeneous space. So you see from one point, and you can get any other points by the isometry. So the all isometries give you a group, the group G, and then you can look at at one point you look at the elements, so fix that points. These give you a subgroup. This one called the stabilizer or the isotropic that points. And the manifold can be written as the quotient of these two groups. So this is for the homogeneous space. Biquotient, so we take two different subgroups, and K and H. So here you have the space, right? And then you just then you just take another quotient by another subgroup. Then you can put some metric, a natural metric on this manifold. So this give you. So for the biquotient, we have more examples. We have two different examples. So one is given by the Eisenberg, an example in dimension 6, and an infinity family in dimension 7, and another space called the Bazakin space. Bazakin space is in 13 dimension, so we only have infinity family for the positively curved biquotient. Okay. Yeah, I think sometimes, I mean, so, yeah, so now you can hear me again? Yeah, sure. So, which page I have to go back? Hey, Jonathan?
Yeah.
Yeah,
There's like even more examples. That's why we couldn't hear.
Oh, you went, okay. So, this one? Okay, that's good.
Yeah.
Okay, so for yeah, I think maybe 5 years ago, so we have two more examples in 7 dimension. So one is given by the T1S4. So the T1 one is given by the group Wadayani. So this manifold is the T1S4. So what is S4? And we have S4, so this is a sphere in 4 dimension. And then we have the tangent space. So we know at each point the tangent space is R4, and we can look at the unit sphere in the R4. So you see the unit sphere has the sphere with radius 1 in the tangent space is 3 sphere. So this means at each point on S4, we look at we have a 3 sphere. So the total dimension is 7 dimension. So this is called the unit tangent space of S4. This one is not the standard one. So this means you have the different smooth structure than the standard one. So this is why we call exotic. So this is the exotic T1, and so this one has a cohomogeneity. We look at some properties for this metric or for the load. So this one has a positive sectional curvature certainly, and also this one has the cohomogeneity 1 action. So the cohomogeneity 1 action just so you see in the homogeneous space. So you can go from one point to any other point. So you can look at the orbit of one point. So the orbit is the whole space. The cohomogeneity 1 action just means, so if you look at one generic point, you look at the orbit by the asymmetric action, so that the orbit is actually a hypersurface. So this one is one example in an infinity family of manifold. So for this family, so we don't know any obstruction to the positively curved metric. And all of them have the cohomogeneity 1 action. So this is the first example. So we don't know any obstruction, but if you want to show the positive, if you want to show this guy has positive sectional curvature, then you have to construct the metric. So this is the first example. So they can construct the metric and compute the curvature, and it's positive. And on the same manifold, so there's another metric. So by the Derichot, the Derichot has another metric on the same manifold, also has positive curvature. So this is one example in the exotic T1S4. Another example is also the exotic example. So this one is the exotic sphere. We have the S7 in 7 dimensions, the standard one. The exotic sphere just means you have the different smooth structure. So this is a work by John Milner. Okay, so for one exotic sphere, so actually there are 28 exotic spheres in 7 dimensions. So for one of these, Peter Peterson and Wilhelm proposed a construction for this exotic sphere, for one exotic sphere with sectional curvature. So this manifold is quite interesting because on the same sphere, so Grumo and Mayer, so they showed there are non-negatively curved metrics, and this by Peterson and Wilhelm. So this one is actually by deforming the metric, deforming the Grumo and Mayer's metric, and to get the positive curvature everywhere. Okay, so this is examples for the positively curved manifold, and then we can look at the manifold in the with non-negative sectional curvature. For the non-negative sectional curvature, so I'm happy because there are many examples. The problem is the construction is very limited. So this is So this is a construction for the non-negatively curved manifold. So first, you can get a new example by taking the product. So you have S2 curved S2, and each one has a round metric or even positively curved metric. If you take the product and you put a product metric, then this guy has the sectional curvature bigger or equal to 0, but they have positive curvature. And another large class, so given by the homogeneous space or by quotient. So this is another class. Or in general, so we have a general construction from the homogeneous space and the biquotient. It is called the Riemannian submersion. The Riemannian submersion. So this is the definition for the Riemannian submersion. If you look at the curvature condition, so the P is the manifold you want. So this is a sectional curvature, and this plane. So because the sectional curvature, the sectional curvature. So you look at the two planes. The two plane is the span between vectors x and y. So this is a manifold you want, and you look at the sectional curvature of the two planes spanned by x and y. So this one actually is given by the old manifold. So this one is the old manifold. You already know it has the non-negative sectional curvature. So this is called the O'Neill formula. So the O'Neill formula tells you the new manifold, the sectional curvature of the new manifold, so actually given by the old plus a non-negative term. So you see the curvature cannot decrease. So this means if you have the M is positive, non-negative, or positive, then the new manifold has non-negative sectional curvature. So this is for the homogeneous space biquotient or for the Riemannian submersions. And so this is so we have two constructions here. So now we want to look at new constructions. We just keep this. Okay, so the new method. So one is called the Chigger's gluing method. So the Chigger's so we have the compact rank 1 symmetric space. So we have the projective space and the Cayley, and then Chigger has a method to glue two compact rank 1 symmetric space and put a metric with non-negative sectional curvature. This is the Chigger's gluing method, and this method we have new example, and then Group and Taylor. So about the 2000, the year of the 2000. So they generalized the Chigger's gluing method. This is called the Group-Taylor's construction on the Cohomogeneity manifold. So we have talked about the Cohomogeneity manifold. So now we look at the definition for the Cohomogeneity manifold. So you see this guy is quite interesting. So a Riemannian manifold is called a Cohomogeneity manifold. So if there exists a compact acting on M by isometries, and the cohomogeneity of this action, so this is the dimension of the obvious space. So you see so this one, so the cohomogeneity means the dimension over this M over G, so equal to 1. So this just means, so if you look at the orbit of a point, so a hypersurface in your manifold. So if you have the cohomogeneity equal to 0, this is exactly the homogeneous space. So then you can signify the cohomogeneity as a generalization of the homogeneous space. Yeah, some people call the cohomogeneity manifold as almost homogeneous. Okay, so now we look at the obvious space. So the obvious space, you know the manifold has dimension equal to 1, and we have the manifold is compact. So the M quotient by G is a compact manifold. So in one dimension, we only have two examples. So one example is given by the S1. So here, so the circle has. So if you are in this case, then M has infinite group, and also has non-negatively curved metric. And you see the fundamental group is infinity, so this means there's no chance for the positively curved metric, because for net mass, we know that the positively curved manifold has finite fundamental group. So this case is not quite interesting. The most interesting case is, so we have the interval here. So for this interval, so we look at this is, and so for this one, we can look at some simple examples for the Cohomogeneity manifold. In this case, we just go back to our favorite example. So this is S. So for the S2, so we have, this is S2 here. So this is not a very round S2 like this one like a football or the soccer. And then we have action. So this is called the SO2. The SO2 is the rotation in the two plane. So you see, so if we fix, so this is the equator for the S2. So we can rotate along this equator. So this means any points, so we are go by this rotation. So to any other points on the circle here, right? The blue one. And also, so if you have this point here, then by the rotation you can get any points on the green circle here. So you see, for each object, so you see the sphere has dimension equal to 2, and the object is just the circle here, the green one or the blue one. So this guy has dimension equal to 1. So this is actually hypersurface. In some sense, the co-dimension is equal to 1. So this is a co-dimension 1 object. And so there are two interesting. So you see, for any points on the sphere, you can only look at this right equator here, because you can get any other point by the rotation. So there are two special points. So this is called B minus and B plus. So you see, if you rotate around these points, so this one actually is fixed, also fixed. And this is called the fixed points. And then we have this property here. So this is, we just summarize the S2 action on the sphere. So we have this called a singular orbit, because this one has the different from the there's fixed points, and the principal orbit. The principal orbit is just the one has a bigger dimension. So you see this one just the circle here, the green one and the blue one. And then you can look at the two disks. So you see from here you have the two different disks. So around this D minus, for example, you have this one here, right? This is a disk. And another disk is given by the green circle, and the center of the disk is a B plus. And so you can think about the S2 by gluing the S2 by gluing these two different disks along the circle here, along the principal orbit. And then you can compute the asymptoty. So the asymptoty means the element fix the points. The element fix the B minus and the B plus. So the asymptoty group is the whole group. And for any other points, so different from the B minus B1, so you see every element will move this point to another point. So you see the elements fix these anti-elements. So you have the H equal to 1. So this is the action of the SO2 on S2. This is Cohomogeneity 1 action, because the orbit is given by this interval here from B minus to B plus. Okay, then we look at the curvature property. So we just go through. Okay, so we just look at the curvature property here. So you have this is a special vector field. This one is called the Killing vector field, and then you can look at this Killing vector field. This one is a function along this interval. So here the Killing vector field is 0, and here you have the different length of the Killing vector field. This gives you a function along the t. The t is a parameter, so along this right half equator here, so half parameterized by t, and this is a function of t. So now we go back to the curvature property. So there are certain conditions. We look at the sectional curvature. So you see, we only have so if we go back to the picture. So we only have one two plane. So it's spanned by the tangent vector along this t direction. So it is called the big T. and also the tangent vector, the tangent to the circle. So this is a killing vector here. So you see, we only have two planes, and this one spanned by T and T. So if you compute the sectional curvature, and so you see the sectional curvature actually is given by the second derivative of the function h here, but you have a negative sign here. So if you want the curvature to be non-negative, so this means you need this term to be non-negative. And so if we look at the example for the one sphere, so you can compute the t, the length of the equator, the half equator is equal to pi, and the function is given by the sine of t. Then you just plug into this formula, you find out the sectional curvature is equal to 1. Give you the one sphere. So this is one simple example for the cohomogeneity one manifold, and also we know how to study the curvature property. And the curvature is given by the function and up to the second order derivative. Okay, so this is a general. This is a picture for the general cohomogeneity manifold. So you have one singular orbit, and you have another singular orbit, and then you have the entropy group, the stabilizer, and you have another stabilizer, the entropy group here. And then you see this, you have a geodesic connecting the bundle. So then you can glue them along the disk. So this gives you the whole manifold. So yeah, this is just a picture regarding the cohomogeneity one manifold. And you see, if you want the cohomogeneity, so this is actually the cohomogeneity one manifold. And another way to write the cohomogeneity one manifold, so this is called the group diagram. The group diagram, so you have, so this is the isometry group for your manifold, and then you have the entropy group for the singular orbit. In the S2 case, so this is just the S2 and SO2 and SO2 for the fixed points. You have the H, so this is called entropy, and you have some relations for these two. So the quotient of these two groups has to be some sphere. Okay, this is called the group diagram. So for each cohomogeneity one manifold, so you can got the diagram by the group action, and also from the last slides. So you see from the last equation, so you can, if you know the group diagram, then you can got the manifold by glue these two. So you see you have the one-to-one correspondence of the manifold and the group diagram. So for the theorem, so the theorem for the group angular, so they actually has a non-negative curved manifold for a large class. So a compact cohomogeneity plus minus smaller or equal to 2 has an invariant metric with non-negative sectional curvature. So what is the meaning of this? So the singular orbit, so we know the principal orbit has dimension equal to n minus 1. So if your manifold, the n dimension, the principal orbit has dimension equal to n minus 1. So this condition just means you have two special singular orbit. So that one, so this 2 has dimension n minus 2. So the orbit is n minus 2 or n minus 1. So if the group action has this property, cohomogeneity one manifold has this property, so they showed there is an invariant metric with non-negative sectional curvature. This gives you from this theorem. So there are many examples from this theorem, from this construction. So one is insertion. So we have the equilibric sphere. So 10 of 14 equilibric sphere by this property, and also other examples in this construction. So this is a new example the new construction for the non-negatively curved metric. Hey, Jonathan. How many minutes we have?
It depends on you guys how long you want to go, and you mentioned that you do have more time, so he could conclude now.
Okay, so actually, yeah, maybe I can conclude in minutes. Is that okay?
Yeah, that's fine. Yeah.
Okay, so you see for the for the non-negatively curved manifold, so we have a new construction. So this is for the group dealer construction for the Cohomogeneity manifold, and there's a theorem here to give you a lot of example. Okay, so the question is, so we know for the homogeneous space, and for there's a natural way to pose an environment metric, and the environment metric has non-negative sectional curvature. So group and dealer, so they ask the question, so is this true for the manifold? So that means, so for any cohomogeneity manifold, we have environment metric with non-negative sectional curvature. The answer to this question is actually no. So you see the difference from the homogeneous space. So actually for each pair, so this gives you the co-dimension of it. So if the co-dimension, so if this pair is not equal to the 2, 2, so this case, so when the L minus and L plus is equal to 2, 2, so this is covered by the construction by group and dealer. Other than that, so this means for any case different, for any case not in their theorem, and there exists infinity many cohomogeneity manifold, and on this manifold there's no environment metric with non-negative sectional curvature. So this gives you the obstruction, so non-negatively curved cohomogeneity manifold. So for this, so for from this obstruction, so there are examples called the exotic sphere. So this called that one is dimension 9 and up. This is the exotic sphere has a cohomogeneity action, but there's no trick with non-negative sectional curvature. So this is a kind of bad news for this exotic sphere. And so in my thesis, I just generalize these examples to a larger family. Okay, so now we look at how to show. So there's obstruction for the non-negatively curved metric. This is a strategy for the non-negatively curved metric. So we see in the S2 case, so you see the metric. So we can fix a normal geodesic, so like the half equator in the S2. This is a geodesic in general by T between two singular orbits. And then we have the killing vector field along this geodesic. For each killing vector field, so we can look at the length, the length for the killing vectors, or even the inner product between the two different killing vector fields. So these are of functions in T. So for example, for the Fourier sphere, so there are 6 different functions. Then we look at the certain properties because the metric has to be smooth. So now, now look at if you want the non-negative sectional curvature, then you have to choose 2 planes, and then you compute the sectional curvature for these 2 planes. So this give you the relation of these functions up to the second order derivative, and you want the sectional curvature bigger or equal to 0. So this means you have the differential inequality for these functions and up to the first order and the second order. Then you have the differential inequality for example, for 6 functions or 3 functions. Then you just choose a suitable 2 planes So this is a difficult step. So you have to choose the right two planes, and you got a contradiction from the two different differential inequalities. So for example, one tells you a term bigger or equal to 0, and you may got this term smaller than 0 by another two planes. So this gives you the contradiction. Okay, so this is just the idea, so how to show the obstruction. Okay, so yeah. Okay, so there are more. So we see for the Cohomogeneity manifold, we have a very nice theorem. So by Groove and Wheeler, for a large class, we have the curved manifold, and also we have the obstruction. So that means the manifold do not have a non-negative, do not have invariant metric with non-negative curvature. So this raises the interesting question. So how large is the Cohomogeneity manifold with a non-negative sectional curvature? So then we want to look at interesting examples. So there are classification by Cohomogeneity. So he classifies a simply connected Cohomogeneity manifold up to dimension 7, and also Schwarzkopf and Quistab. So the partial classification if the manifold has some properties, some nice geometric properties. There's another classification. So yeah. I just at the end I just want to mention another classification. So the classification, so here if we look at the compact and simply connected remaining manifold it has some simple cohomogeneity 1 action with F2 3. So you can go back to the last slide to see the definition for the S. So this condition just means so the action is not very complicated. So the action is simple. Then I have the classification. So the manifold is actually equal. So this manifold is actually diffeomorphic to space with asymmetric action, and also the action determined. So the equivalent diffeomorphic means the action is also determined. So if you look at this classification, we only have the sphere, compact, and the harmonic projective space, Taylor plane, and the Grassmannians in this classification. So you may want to know. So what about? So this is for the S smaller or equal to 3. So for the S equal to 4. So actually we have the construction. We have the obstruction here. So for the Korean sphere, so this one has actually S equal to 4, and we know there's no invariant metric with non-negative sectional curvature. Okay, so. Yeah. Okay. So this is the end of the talk, and thanks. And this is the reference. So if you are interested.
Yeah. So thank you very much for the talk. And University of Ghana, do you have any questions to ask Chenxu? No. Hello.
Yeah.
Yes, we are here.
Okay.
I'm asking. Anything to say? Nothing to say except thank you very much.
Okay.
Enjoy
Okay.
the seminar.
Okay then. Yeah. Thank you then.
Yeah. Thanks.